So welcome to my video on escape velocity. So in this video, we're pretty much going to explain why there's not much hydrogen in the atmosphere. Like hydrogen and helium makes up quite a bit of the universe. Well, if you minus dark matter, dark energy, makes up quite a bit. So why don't we have so much of it in our atmosphere? Why does it escape? So we're going to go through what this escape velocity is without going into the technical jargon. So if you're just trying to learn a bit of an astronomy without all of those fancy terminologies, this is the video for yourself. So we're going to go right from the start. So our atmosphere is made out of pretty much quite a few gases. Some of them are very lightweight. Some of them have a more higher weight. We can actually see the relative atomic mass of many of the gases. So hydrogen over here, lightest element, 1, going up to oxygen, 16, and so forth. You've got different types of gases that make up our atmosphere. The two most common ones is nitrogen and oxygen. Nitrogen being the most, around about 72%. Oxygen being around about like 18-ish or they both nitrogen and oxygen make up 99% of our atmosphere, which is pretty funny because that is not what is seen in other parts of the universe. So we're going to be talking about them. So there's kind of carbon dioxide and greenhouse gases, ammonia, methane, and so forth. And all of these types of molecules in the atmosphere possesses approximately equal kinetic energies. So they all have equal. Now, if you remember about kinetic energy is half mv squared. Now, what this basically means is if they got all equal, like round about equal kinetic energies, and they all have different masses, so that mass and that kinetic energy, their velocities are all going to be different. So they're all going to have different velocities. Now, just to spoil it right over here, right? The lower their mass, the quicker they can move, okay? So we could put it in simplistic terms like that, okay? So as a result, at a given temperature, lighter molecules with smaller masses will have higher velocities, higher speeds, compared to heavier molecules. So the heavier ones, as you see that down over here, are going to have, less velocity. And if they got less velocity, they're not going to be able to escape the Earth's gravitational pull. Now, that's what escape velocity is. Escaping the Earth's gravitational pull. Now, I've got some figures over here. So I believe that this is the escape velocities for the sun, all the way to Neptune. The Earth is, the moon is even there. Moon hasn't got quite a lot of it. It has a low escape velocity because it has a low gravity. If you remember the curvature of space, like if you put a mass and it curves, the curvature of space is what gravity is, okay? So if you got less mass, the sun is being the most out of the list. That is why it has the highest escape velocity. You have to achieve a really high speed to escape the gravitational pull. That's why with rockets, they don't go directly upwards. They go kind of like in the curvature because they're trying to approach the escape velocity to escape the Earth's gravitational pull. Now, the average kinetic energy that they have depends on their atmospheric pressure. Now, there's a relationship between kinetic energy, so half mv squared, and this equation over there, 3/2 kT. Now, I'm not going to go too much into depth about this, but that's the Boltzmann constant, and that's the temperature. So there's a relationship between temperature and velocity, okay? The hotter it is, the more kinetic energy you're going to get. The colder it is, less kinetic energy you're going to get. So in a warmer atmosphere, the gases are going to collide with a higher velocity compared to a lower one. So just making it simple, just like that. If you travel far, if you are hot enough, you're going to travel faster. If you travel faster, you have a greater probability of escaping the Earth's gravitational pull. Now, the reason why I'm saying probability is because we're talking about average kinetic energy. That doesn't mean all the gas molecules are going to have the same kinetic energy. Some of them are going to travel faster, some of them are going to travel slower. So the hotter it gets, the more the proportion of gas molecules that will have that specific speed, that specific velocity to escape the Earth's gravitational pull. Now, just doing some simple math over here, okay? So hydrogen molecules, we looked at hydrogen molecules, okay, will move on average 4 times faster than oxygen molecules, okay? And it's all to do this. So this is the relative atomic mass, okay? We need to have the actual molecular mass, but doesn't really matter too much. It depends on the number of neutrons and protons. So this is just showing the number of protons. There should be a molecular mass as well, which combines the number of neutrons, because neutrons and protons have pretty much the same mass, pretty much. Now, so hydrogen molecules, if I write hydrogen, so if you did your chemistry, you remember hydrogen, you could write it like this, 2, 1. Okay, that's one form of hydrogen. There's different forms of hydrogen. And oxygen is a molecular mass of 32. Now, there's a 2 and a 32 in difference, okay? Now, if you rearrange this whole equation over there, what it will show is that the oxygen molecules, okay, are going to travel 4 times slower, because they're heavier, 4 times slower than the hydrogen, because there's a v squared. Okay, you could do the math and rearrange the equations and work it out yourself. So it's not like, okay, if you got 2 times less mass, you're going to go 2 times faster. There's a velocity squared aspect to it. Now, the molecules that escape are going to be on the upper atmosphere. So if I drew out a planet right over there, and this is the upper atmosphere, what we are concerned for you to escape, it matters about your velocity up over there, not your velocity down there, because your velocity down there, you're not escaping the Earth yet. Okay, it matters about what velocity you achieve at the upper atmosphere. If you achieve enough velocity, escape velocity, you'll be able to jump out of the atmosphere and escape the Earth. So the escape velocity depends on the mass, because obviously the higher your mass, the more gravitational pull you have. And it's also dependent on the heat of the actual place. So being a star or being a planet, because the hotter it is, the more proportion of gas molecules that will have the required escape velocity to escape the gravitational pull of the star, or would it be like the gravitational pull of the planet? So basically, the cooler it is and the higher the mass it is, the more gas molecules it's going to attract, because the cooler it is, it won't have enough velocity. The higher the mass it is, the more gravity it's going to have. Now, on Earth, the average velocity that the oxygen and nitrogen traveling at haven't got sufficient velocity enough to escape the Earth's gravitational pull, which is why we see so much oxygen and so much nitrogen in our Earth's atmosphere. Now, just to reiterate, if I took generally hydrogen has enough escape velocity to leave, okay? Because all the hydrogen molecules are not traveling at the same speed. Some of them are traveling with greater velocities, some are traveling with lower velocities. That's why we say average, we take an average, but some of them are going to have the necessary escape velocity to escape. So we're actually losing hydrogen. So when the hydrogen molecules on the upper atmosphere, just where they're about to escape, achieve that escape velocity, they are going to escape. So this is why the amount of hydrogen gas, the percentage of hydrogen gas, is around about like 0.0000055%. It's ridiculously small, even though hydrogen gas is pretty much what makes up the majority of the universe. If you exclude dark energy and dark matter, it's making up what the majority, especially with stars, it makes up like 80%, 70 to 80% of stars, which are converting the hydrogen into helium. So both of these gases are in, like helium and hydrogen, are very light molecules, which is why you don't see much of it on the Earth's atmosphere. So you could see over here, the Earth's escape velocity is around about 11. So this is what the minimum velocity you need to achieve to escape the Earth's gravitational pull. Now, looking at Jupiter, which is, some would say is a failed star, it's has an incredible mass, has an incredible escape velocity, which is why when you go, if you went to hydrogen, Jupiter hasn't got so much of a temperature. It's around about surface temperatures around about 100 kelvins. Um, you know, the hydrogen molecules in Jupiter is traveling around about 1 kilometer per second. On Earth, they travel around about 2 kilometers per second. On Jupiter, they travel very, very slow. And then they're no way near the escape velocity to escape. So it's what Jupiter has done is it's retained the majority of its hydrogen, which is why 90% of it is hydrogen and 10% of it is helium, because yeah, those are the two. And there's a few other elements also, but not much. So what is giving this hydrogen the necessary kind of energy to escape? Well, some of it is from solar winds from the sun. So these are pretty much a stream of particles. It could be primarily electrons and protons. There's alpha particles. There's quite a lot of stuff. But these particles are given off by the outer surface of the sun, and their speeds range quite a lot. So their speeds range from 300 kilometers per second to 800 kilometers per second. So they're traveling extremely, extremely fast. So because they're traveling extremely fast, they have a lot of kinetic energy. So when these particles reach the Earth and they collide with the hydrogen gas on the upper atmosphere, they're going to give some of that kinetic energy to the hydrogen, allowing the hydrogen to then escape. Now, the current leakage rate is around about 3 kilograms per hour of hydrogen and only about 50 grams of helium, which explains, look, you got 3 kilograms worth of hydrogen escaping and only 50 grams worth of helium. Why? Because helium has quite a lot of mass when you compare it to hydrogen. Now, if you enjoyed this video, I ask you to subscribe, like the video. It helps out the algorithm. Also, check out my Patreon. I'm trying to do live lessons for free for my students. But I wish you a good day and take care.